Ladies and gentlemen, our program is about to begin. Please take your seats. Thank you.
CoreOS has been one of the companies helped creating this whole new category around containers and distributed systems. We've built a number of the open source technologies that are used by kind of every major project emerging right now between etcd, container Linux, or Linux distribution, Rocket. It's just kind of helped foster along this whole ecosystem.
So 1.6 was released recently, and so this workshop is interesting because there's going to be an overview. I hope there is a difference between the old version and the new version and everything that was added on.
CoreOS has been with the project for a long time. They've been contributing all over the place, from things like governance and process, security, node work, container runtimes, storage, some networking stuff. They've contributed now with their idea of operators. So it's been a really big collaboration, and we really appreciate those guys being part of the project.
I think that the strength of Kubernetes is primarily grounded in its openness. I think that one of the things that we can squarely point and attribute a lot of the success of the project to was the fact that it was very accepting of other folks.
I think we do a very good job as a community of involving vendors in the discussion of what Kubernetes should be, what Kubernetes is, what Kubernetes should become.
The space of things that people need to be productive, to use a system like Kubernetes for end-to-end is a huge space.
We've seen just crazy rapid growth and adoption of Kubernetes, especially over the last year or so.
We talked about deployments, and we said the feature set was the same as replica sets.
So I think the really fundamental question that we need to answer is, how do a community member, how can you come to the project and file an issue that gets some heated debate, and if you don't like the answers and the decisions that are being made, how does that escalate?
I like the idea of a meritocracy, where you're not a BDFL because you initiated this. You have an opportunity to rise through the ranks, and by merit and contribution and strength of what you do, step into a role of authority on the project.
Please welcome Brian Redbeard.
And welcome back to all of you. We're very, very excited to have you here today. We're at the point of what I would say half full. We've gotten through part of the content, but we still have a lot more and a lot of exciting things to look at. I am sitting through some of the technical talks yesterday, always the things that are near and dear to me. Even I am learning things here, and that is exactly the thing that I cherish. I look forward to having conversations with all of you today and working through a lot of the technical discussions that we want to have and figuring out what are the pieces that come next. I would also like to take just a moment here to recognize some of the folks from the CoreOS staff who, brought all of this together. The folks from the design team, the folks from the marketing team, the folks from the actual community teams who made sure that everyone was aware of what was going to be going on, went out and solicited some of the best speakers to come here and talk to you and share their ideas. This is exactly the thing that gets me excited to be here. And I'm not alone with that. You know, the next person who's going to be coming up here is Brandon Phillips. He's the CTO of CoreOS. He is one of the pair, one of the individuals in that initial kind of embryo of thinking about what open source could be in terms of securing the internet and making sure that everything, all of the pieces that we work with on a day-to-day basis could be automated as much as possible. And over the last 4 years, there has been a lot of work in both the commercial products, but more importantly, the open source side of things. And that's what Brandon's going to be sharing with us today. So without further ado, let's get a round of applause for Brandon Phillips, the CTO of CoreOS, who's going to be sharing the history, our shared history of open source.
All right. Good morning. Good to see everybody. So yesterday, Alex talked through some of the things that we're building at CoreOS, notably Tectonic. And what I wanted to go through was talk through some of the communities that are around Tectonic, the things that enable us to build the product. And it kind of falls into all these major categories here around automation, how we're building things like etcd as a service and Kubernetes as a service, portability, of course, the container story that's really brought us here today, the excitement that a lot of us found a few years ago, monitoring, governance, and all the applications that are starting to be built on top. So why build open source? Like, what is the motivating factor for all this stuff? What do we think about? What motivates us to do this? And really, I like to think about open source as almost being necessary today when you're tackling really massive problems. So I like to talk about it this way. There's 3.5 billion people on the internet, and there's about 30 million of us, people who are software engineers, IT practitioners, developers. And so we're super outnumbered. There's way more people using the internet than know how all of the plumbing and everything works underneath it. And so some people may say, well, we can just train our way out of this. It's no problem. We'll just make more engineers, more IT people. Unfortunately, we're adding like 250 million people to the internet every year. So this is a problem that's pretty intractable. And so these people coming onto the internet, what they're doing is they're using their phones and their computers, and they're giving us onto our servers, the ones that we maintain on a day-to-day basis, all the critical information, their documents, their commerce, their communications flow through these servers. And so we have a responsibility to build software systems that do right by everyone, do right by all these people coming onto the internet. So there's about 100 million servers worldwide. The number is probably north of this. It's really hard to get a good count. If anyone knows a source, I'd love to find one. I tried to find one. But it's, let's just say, south of 1 billion, north of 100 million, all right? And so that's a big problem. There's a lot of stuff that needs to be built. And really what got us excited, a lot of us here in the ecosystem, was this idea of a portability layer. There's a lot of different places you can put your servers. You put them on-prem, you put them on public cloud, and making sure that the applications we build can move around between them is pretty important. So 3.5 years ago, there was this emergence of this, what can be called like kind of a compute portability layer, a way of running applications that abstracts it away from the way that the servers were created. And it kind of started for us with the creation of CoreOS Linux and the Docker engine. Of course, we renamed CoreOS Linux to Container Linux, and so I'll continue to use that term. I know it's tricky. I hear a lot of people trip over it. I trip over it myself. But the idea here is that we have a bunch of servers, and you move, whether it's on-prem or on cloud, applications between those servers really easily using these technologies. And these were built by teams of people, not from individual companies. We rely a ton on Go, which was introduced by Google. This is some of the folks from the Go team, along with the Coros team about 3 years ago, in front of this wonderful RV that we had at the time. And similarly, the Docker team, there's a lot of familiar faces in there, built by a wide community of folks. You can see Brad Fitzpatrick and myself. This is a really early photo of one of the early Docker hack weeks. And so this whole thing emerged because of a bunch of people coming together, sharing ideas, and building this stuff. And so I wanted to give a little bit of an update, like what's happened recently, what's changed since the emergence of that several years ago. So why did we build Container Linux? So we built Container Linux because we saw a need around the container ecosystem was pushing the Linux kernel really hard. And with something pushing the software really hard, you need the latest software, the latest open source software, into the hands of the users for performance reasons, security reasons, et cetera, and for wide platform support, because we wanted to ensure that this compute portability layer actually went everywhere, across all the clouds, across all the places that people run compute. And so the opportunity that we saw was to build a new open source project for a Linux that could move faster. And that's what we built and continue to build with Container Linux. And I think the success really can be shown with where all the places that Container Linux runs today, whether it's on VMware or on regular bare metal servers or across all the public clouds. And so this is an ongoing mission. Like any open source project, we continue to work on this. And so up next, I'd like to have Mark and TJ from Oracle. We're working with them to bring Container Linux to yet another platform and the rest of our products as well. So Mark and TJ.
Brandon, Hassan. All right, good. Thanks so much. Good morning, everybody. Great to be here. I'm Mark. This is TJ. We're from Oracle, somewhat obviously, as the sign says, and Brandon just said. We wanted to give you 2 quick updates about what we're doing in the container ecosystem in general. We're really excited about what we're doing with CoreOS. So number 1, we've partnered with CoreOS to bring Coros Container Linux, I will not stumble on that, to Oracle's cloud infrastructure platform. We'll talk about that in just a second. And also, we're just going to be generally investing in the Kubernetes ecosystem and open source as well, which we're super excited about, and TJ will talk to you about. So it is probably worth taking a quick second, I suspect, at this audience in particular, to ask, like, why is Oracle here? Why are we on stage talking to you? And why are we talking about containers? I don't think most people realize this, but Oracle's invested very heavily over the last few years in becoming a hyperscale cloud provider. TJ and I very personally have lived through that. And at this point, we have, we think, a really fundamentally better true public cloud optimized for container workloads. Notably, it is bare metal capable. We did that for a very specific reason. When we started down this journey, we kind of took a look at the market and said, well, what's the strategic bet? What are people really going to be building next-gen workloads on? The answer was, frankly, pretty obvious, which is containers. And there's a lot of talk around the developer gains, productivity gains, et cetera, that people get when they move to a Dockerized or containerized environment. But there also is this giant amount of efficiency and density gains you get. So we built the only public cloud that lets you get just-in-time bare metal provisioning, honestly, to get containers and get a really good story for container workflow. So, cool, we got this awesome cloud. It's really good at running containers in general. Now we're bringing an awesome Linux to it. So we recognize that, CoreOS Container Linux is basically the de facto standard now for what people use as a host target to deploy containers on. So it makes perfect sense. We need to work together. So we're very excited. In a few months, you'll basically see certified images from both us and CoreOS working together on that platform. So that's one. Additionally, we've entered the Kubernetes space ourselves and been, I don't know whether there's dipping your toe in or whatever internally, and using Kubernetes a lot to power some of our own cloud services. And so we just think there's a lot of opportunity to help the community truly in the open source ecosystem. And so to talk a little bit more about what we're going to be doing with Kubernetes, TJ?
Right, so we're starting with deploying our own new cloud native services on top of Kubernetes, and then we're going to invest in you and the broader ecosystem and the community heavily. We understand what that means. We want to be good open source citizens. We're getting value from you. You should get value from us. So I see a ton of similarities with this community and the community that I previously led with Node.js. There's incredible velocity in the community, there's impressive adoption rates, and enterprises are wading in head first. So at Oracle, we think that we have a great experience delivering distributed systems at scale. We have a strong focus in security and just a little bit of enterprise as well. We think we can contribute back to this community significantly. So over the next few months, we're going to be slowly phasing in our efforts, and we're going to start by earning our stripes and participating in the community by answering questions on Slack, Stack Overflow, triaging issues on GitHub, improving documentation. We want to make it clear that we are going to earn our spot in your community, and that it takes more than talking about it, it takes action. We're also going to be ramping up our engineering efforts. We're going to have our own cloud provider, obviously, so using Kubernetes on top of Oracle Cloud Infrastructure is going to feel natural. But we also know that what's good for the community is good for Oracle. So we're going to participate in as many special interest groups as we can. We're going to take our experiences of developing Java and the high bar we have for quality releases in terms of testing and participate in the special interest groups for testing and improving that ecosystem, as well as we have a keen interest on federation and being able to perform clusters in a global fashion. So we're going to take all of those things, participate in it, and turn it into real action for the community, tangible action for the community, and we're going to do it together. So we're really excited to participate with you guys.
Cool, thanks. So I think we covered everything we need to cover. I'll nutshell this up real quick with this closing slide. We have an awesome cloud infrastructure platform. We're bringing an awesome Linux to said cloud infrastructure platform. We're investing heavily, or we'll start investing heavily into Kubernetes. We're going to cut wood and carry water for a while, and then we're going to show meaningful traction there. And then lastly, I'll mention that we're building a bunch of managed services as well on our cloud services platform around the Kubernetes and container ecosystem space. I'll just leave you with one quick call out. The worker guys have a booth downstairs. They put together a nice promotional to get you a couple clicks, and you get a Kubernetes cluster up on bare metal cloud, so you can check that out. So thanks.
Cool.
Yep. Good.
Thank you. Awesome. Thank you, Mark and TJ. I think the continued interest of a number of organizations inside of Kubernetes just reflects the people and the customers and the users that are getting on board with the whole container and orchestration system. And to that end, a few years ago, in 2015, CoreOS and a bunch of other industry leaders created a foundation called the Cloud Native Computing Foundation to kind of foster the creation and promotion of these technologies. It's container packaged, dynamically managed or scheduled, and microservices-oriented technologies. And so hopefully some of these logos look familiar, particularly Kubernetes, but CNCF hosts a number of these projects, holding onto their IP, providing budget for marketing, et cetera. And so what's happened recently is that some new projects have been added to the CNCF, notably Rocket, Containerd, and CNI. And I wanted to talk through what each of these mean and why they're important for the ecosystem and why we've been involved. So CNI is a system that originally was called the Rocket plugin system for networking, but we renamed to Container Networking Interface. And really what it's enabled, and through its adoption inside of Kubernetes, is that people have a wide number of options that work well on-prem or on cloud for managing networks, particularly for Kubernetes, but can be plugged into a lot of different systems as well. So you're seeing kind of an explosion of various projects and vendors being able to plug into the Kubernetes ecosystem through CNI. So that's now part of CNCF, and it has become a big community project with a lot of different folks involved. The other bit is Rocket had its first release, Rocket 1.2.6, underneath CNCF a few weeks ago. We added a bunch of new contributors. There's some new design docs on how to do VM isolation. And then I'd like to give a round of applause to Tino, who was the first community member to pilot and do the release on his own. So round of applause for Tino for that work. So some other work that's been going on. We've had a huge focus on monitoring at CoreOS. We have a few folks that had some office hours around Prometheus yesterday. But really, we think of it as if you have no idea what's going on in the system, it's probably not a production system. So you need monitoring through and through. Prometheus is an open source project, part of the CNCF. If you haven't used it, please check it out. But it allows you to collect metrics off of your applications, integrate it into Kubernetes, and then have a query language to do rates or bucketing of those metrics. And so the alpha of Prometheus 2.0, which the team has been hard at work on, the wider community as well, has two major features. It uses way less memory and an order of magnitude less disk I/O. And so it's hard to see there, but hugging the x-axis are the new versions of Prometheus. And notably, disk I/O is reduced by an order of magnitude. This is a huge amount of work, and a lot of measurement and monitoring has gone in to make it happen. So I'd like to congratulate the team on that. It's pretty awesome. All right, so the last bit is around governance services. So with governance, it's about who has access to the cluster and then what workloads are allowed to run on the cluster. This can touch a lot of things, but a system that we built and has gotten a lot of community adoption is Claire, which allows people to essentially do static analysis of the containers that they're about to deploy or that were recently built. Two major things that people have been asking of Claire is Alpine Linux support. Alpine Linux has gotten a lot of use inside of the container ecosystem, and so this is a pretty major step for the project. And we've gotten a ton of contributions through and through the project as it gets integrated into a bunch of different systems, Quay security scanning, but a bunch of different other projects as well. So a pretty major release and a pretty helpful feature for the wider container ecosystem. All right, so the last thing I would like to do is focus on the last 10 minutes or so on Kubernetes and kind of give a state of the union of where the project is, some of the things that everyone has been thinking about, and then make some predictions for the future. So let's talk about sort of the team that has built Kubernetes. So if you haven't been following how Kubernetes gets built, there's all these special interest groups. And there's kind of both vertical and horizontal concerns. A cross-cutting concern might be how Kubernetes is installed, how it's updated, how the cluster is managed over time. And this is a focus of people who are in the special interest group called Cluster Lifecycle. And they have software, not just blanket fiat to figure out these problems, but they also maintain software that helps with these problems, notably kubadmin and bootkube. And so this is a group of people who get together and try to solve these issues. Another, maybe more vertical group of people is the SIG Azure, which comes together to figure out how networking, storage, load balancing plugs into Kubernetes when you're running on an Azure cloud. And then they're responsible for all the Azure integrations. And so inside of Kubernetes, we have a lot of these different special interest groups. And these special interest groups essentially organize into a number of buckets, over 1,500 contributors that have come into Kubernetes that are across a ton of different time zones. And you'll notice that we've tried our best, but really it's difficult to bucket these things into horizontal and vertical. It's just that people are touching a lot of pieces of code when working on these concerns. Now, one of the problems is you have a huge democracy of people, and you want to avoid some of the downfalls of democracy. So this is a kind of humorous thing that happened on the internet. Somebody said, name our boat. And people came up with Boaty McBoatface. Hilarious, but kind of an expected outcome from the internet. If you've spent any time on the internet, look at the front page of Reddit, kind of tends towards trollish meme behavior. And that's because people just left undirected without a project plan will kind of go into areas that are just personally entertaining. So not really a surprising outcome that you ask the internet for something and they give you a meme back. And so when you're thinking about organizing wider communities of people, it's really important that you have kind of a rails or frameworks or an idea of what you'd like to build. It probably would have been helpful if the Boaty McBoatface people had thought about maybe some themes of names that they wanted. And so when we're thinking about the Kubernetes community, we want to create some direction. We have a really good foundation of where it's going. We're trying to manage these systems. We want it to be distributed. We want it to be scheduled. We want to do bin packing, et cetera. But we need to set direction for the longer-term future and how people actually communicate and organize. And so a few months ago, the Kubernetes community asked that kind of a bootstrap committee be created to figure out how all the projects get organized and capture where we are today, how decisions get made today, what sort of decisions need to happen, and then how those decisions end up inevitably coming to a conclusion. And so there's a lot of stuff in here. How is code of conduct handled? What are the policies around releases? How does testing happen? And the recommendation that we had as the Bootstrap Committee was that there should be a group of people that are elected that kind of figure out these concerns, and hopefully they distribute those concerns to other smaller groups with a very clear focus. That's a lot of stuff. The kind of a failing of open source software is where you get really, really strong leadership, and then everything slows down because decisions get made on the timelines of a couple of individuals instead of the timelines of the hundreds or thousands of contributors that are working every day to make the project better. And so it looks something like this. We have all these special interest groups today, and then we add a little steering committee on top that tries to set directions and communicate where the project is going. And the hope is that over the next couple of months, we'll elect these people and get them into place and start to provide better direction. We're doing a great job already, but provide more concrete direction of where Kubernetes is going. All right. The next bit is, I think a lot of us here today are using Kubernetes because it's a pretty high-quality piece of open source technology. And one of the reasons it is because there's a lot of focus on the release process of Kubernetes. There's a 3-month release cycle where features get built, new APIs are designed, et cetera. And these releases are called minor releases. And then during this whole process, people are finding bugs inside of the system as they move it in production. And each of these minor releases are supported by a release team for almost 9 to 12 months, where fixes are being backported, security issues are being backported, and being communicated to the users. This is a pretty sophisticated set of releases and release processes that generally you don't see inside of an open source community. And I think it does speak well to how serious we are about building a product, not just a set of technologies. And so each of these releases is managed by these release teams. And it's all the things that you'd expect: documentation, testing, product management, et cetera. And their goal over this 3-month period is to move from the very first alpha to a stable release while essentially working through this really impossible set of constraints, this kind of triangle of constraints of high-quality release, all the features that we wanted delivered on time. If any of us have been on a software project, who's ever made a software project that had all the features on time, high quality? 0 hands. Good. Smart people. It's an impossible task, and these teams are essentially in charge of making the calls, making the compromises that lead to the best possible piece of software that we can make in a period of time. And then the best thing that I like about Kubernetes as a community is we spend a lot of time not just doing stuff, but reflecting on, did we do this stuff well? What could we do in the future? So every single release has these blameless retrospectives where everyone who is on the release team gets together and tries to figure out how we can do better. And so I'd like to give a quick shout out. These are people going to the Leadership Summit on Friday, which is Kubernetes Leadership Summit. And the people in bold have been directly involved on one of these release teams at one point or another in the last couple of years. I want to give them a round of applause because they've done a ton of work. All right. The last little bit is that in the last couple of releases, we've worked on making Kubernetes security release processes good, ensuring that we can handle security release or security disclosures in a responsible way, get builds done privately, communicate to users in a timely manner. And this has been a really big part of ensuring Kubernetes is a maturing project over time. All right, so I'm going to spend the last couple of minutes here talking through some predictions for the future. I used to work in the Linux kernel community, and John Corbett of LWN, Linux Weekly News, used to do these great talks on predictions of the future. And it's really hard, because the Linux kernel community doesn't really have great feature tracking and initiative tracking. But my job's really easy here today, because Kubernetes has really good, as good as you can get in an open source community, tracking of what everyone's working on, design documentation, et cetera. So my talk will be very similar to John's, but way more accurate because of the Kubernetes community. So first is that we have a ton of APIs that are being introduced into Kubernetes, and those are going to be moving to stable. We have people today that I know are relying upon daemon sets and stateful sets and ingress and third-party resources. And from all the feedback from people beta testing these APIs, over the next couple of releases, we'll see these APIs moving to stable. The next bit is that Kubernetes has a lot of components. We have the schedulers and the API servers and the control plane to the components that run on the individual nodes, like the proxy or the kubelet. And today, they're configured with a lot of flags. Upwards, I think the kubelet has 40 flags today. And it can be pretty difficult to know what the correct values are, what combinations should work together, et cetera. And so Mike Denise and a few other people in the community are working together to make configuration as well versioned and easy to maintain and automate as the resources that you use as users of Kubernetes, which is a pretty big and important part of the project. The next is that we're seeing a lot of people extending Kubernetes, building their applications on top, things like the etcd operator, the Prometheus operator, et cetera. And this will become important as people want to plug in monitoring systems or PaaS systems inside of Kubernetes. And we're starting to see this today with both the introduction of third-party resources all the way back into Kubernetes 1.0, but new alpha features that are coming into 1.7, like API aggregation, which will allow for extension of the API over time. And the reason people want to extend the API is they're building these really cool distributed systems on top of Kubernetes. And they want to take advantage of the command line tooling like kubectl and kubectl edit to manage their systems. They want to take care of the role-based access control and identity management that happens in Kubernetes to control who can view the system versus edit the system over time. And so you're seeing everything from databases to block storages, et cetera, being built on top of Kubernetes. There's this great list. You see a little URL at the bottom. There's a great list of these systems that are starting to be built that we've been tracking. And then the last bit is around monitoring. Kubernetes has some fundamental monitoring today around CPU and memory that's used to auto-scale stuff based on consumption of those resources. But this doesn't really scale over time because people care about more than just CPU and memory. They care about latency. They care about the requests per second that their applications are handling. And being able to plug in different backends to those systems to be able to have application-specific metrics or derivative metrics is going to become really important because one of the things we hear everyone talk about when they adopt Kubernetes is it gives them the flexibility to scale their application based on user demand. And so tying that into monitoring will reduce a lot of the overhead for people who have to maintain these systems. They don't want to get woken up in the middle of the night because some additional demand was put on the system. All right, so I have one last prediction. This one is pretty easy. People are building and running all this technology, and we're going to see a ton of people wanting to come in and learn Kubernetes. This is a pretty common scene if you've been to a KubeCon event. Pretty packed rooms, some people sitting on the floors, and it's because a ton of companies are starting to adopt this technology. And so there's a lot of momentum and need for training people up on how all this stuff is working, which is leading to a lot of jobs. People are moving from one set of technologies to another set of technologies and actually changing the way that their day-to-day work happens. And so the people building and running these technologies actually have a specific job title at Google called Site Reliability Engineers. And I'd like to welcome up Chris, who's going to be talking about what that role is and what they do at Google for these roles. So thank you very much.
Thanks, Brandon. And thanks, everybody, for joining us today. So I'm Chris. I work in the San Francisco office, just down the street. And I've been a site reliability engineer at Google since 2007. And I've been asked to share some thoughts about site reliability engineering and cloud native and how they all tie together. So 3 main topics for today. First, what is SRE? Second, how do containers and Kubernetes and cloud native fit into this? And then third, I want to make the argument that SRE is cloud native and that cloud native software requires SRE, or SRE-like functions. So, could I get a show of hands? Who here knows what an SRE is and what they do? Okay, that's more than I thought. Good. How many of you actually are SREs? Okay, 3 or 4. All right. So we found it was kind of hard to concisely explain what site reliability engineering is and what SREs do. So, of course, we decided to write a 550-page book to explain it concisely. And it came out just over a year ago, and it covers how we think about, design, and run a planet-scale computing infrastructure. And we have about 70, it's organized as a series of essays that are sort of connected thematically with about 70 authors for each of those chapters and 500 plus years of production experience running one of the world's largest infrastructures. So it came out through O'Reilly last year. It's available at fine bookstores near you, or you can read it online for free at g.co/SREbook. So, what does site reliability engineering mean? To put it in one sentence, we're engineers who focus on reliability for websites. Some companies have used this terminology for similar functions. Others call it production engineering, but it's all fundamentally the same sort of thing. We keep software services running. So let's break this down word by word. First, site. This is the most contentious part of the name, because people often ask, why site? Well, it's a holdover from when SRE were the people responsible for making sure that Google's website was running. Nowadays, we're responsible for making sure that Google's software services in general, some of which are user-facing as a website, some of which are APIs, some of which are internal, are scalable, reliable, and efficient. In retrospect, we probably should have chosen a different name, maybe software reliability engineering or service reliability engineering, but they picked that name before I got there, so it is what it is. Next, reliability. This is pretty straightforward. We're there to make sure that the services that run keep running the way that you'd expect them to run. And Ben Traynor-Sloss, who's our VP for 24/7 operations, suggests that reliability is the most fundamental feature of any product, because a system isn't very useful if nobody can actually use it. And then finally, we have engineering. We use math and computer science to make software manage other software so that the services keep working reliably. So let's go and talk a little bit about the life of a program. In the classic waterfall model of software development, you start out with some requirements, and you come up with a design. Then you go off and write some software. That's the implementation phase, and throw it over the wall to QA to test. You declare it done, you ship it, give it over to the sysadmins, and you never think about it again, right? There's some small problems with this approach. First, it assumes that you know everything you're ever going to need the software to do, and that you have a perfect understanding of how the design will fit together. Second, it assumes that you learn absolutely nothing while you're actually writing the code about the problem space. And of course, it never works in production the way it worked on your workstation, but that's up to the sysadmins. In fact, This is so problematic that even the person who first described the waterfall model, Winston W. Royce in 1970, says that it's risky and invites failure. He tells you not to do this in the paper where he describes this for the first time. Okay. So clearly, the way we should do things is agile, right? We do things in smaller iterations. We don't have to worry about, doing the whole waterfall and finding out that we've screwed something up early on in the process. So we're going to get a minimum viable product out the door so that users get value as early as possible. Then we'll incrementally add functionality on in subsequent sprints. Ideally, you're doing the riskiest bits first so that you learn as much as possible about the problem space and can bring your efforts to bear on delivering the software on time, on budget, and hopefully it works. Agile isn't new either. Royce talked about it in the same paper where he talked about waterfall. But even agile development is missing something. Any really successful piece of software spends most of its time being used, not being built. And yet, as a discipline, software engineering spends a lot more time thinking about designing and building software than we do about actually operating it and how it's going to spend the rest of its life. What site reliability engineers try to do, as we put it in the preface to the book, is think about the whole life cycle of software objects, from their inception through deployment and operation, refinement, and eventual peaceful decommissioning. So that operation box there, that tucks a lot of stuff inside. Let's zoom in a little bit. At the heart of everything that we do, site reliability engineering has monitoring as our focus. Because if you don't instrument and monitor your software, how on earth do you know what it's doing? If you don't know what it's doing, how can you make it run faster? How can you make it more efficient and cost less to run? How do you figure out whether it's working or why it broke? That's why we need a distinct function in our organization to think about software reliability at scale. First, make sure that we don't lose reliability in the shuffle when we're building and running software services. If you have an organization that's built of developers first, it's often easy to think about that development stage, but not about what happens after development. Second, reasoning about complex distributed systems is hard. You build up experience by seeing how they fail and working with people who've done it before. It's really hard to teach in an academic program. There just aren't any. Third, we think there's a lot of wisdom to be learned in actually running these systems and in influencing the design and implementation with what we've learned in doing so. So you can sort of see that monitoring is affecting all of these really important things, like data integrity, right? If you're writing data, somebody's pictures or whatever, you really want to keep it working. You don't want to lose them. So, what does any of this have to do with containers and Kubernetes and cloud-native software? So, software used to come in boxes, floppy disks or CDs, and to be run on computers that you could see and you could touch. You have, the mail server running in a closet, or the accounting program running on your desktop. And I spent a lot of the 90s and early 2000s installing software off of CDs just like these onto computers that looked a lot like those. But now, everybody wants to run their software in the cloud. So what's the cloud? Well, if you live in San Francisco, the cloud is right outside. Carl the Fog is our friendly gray overcast, and he's decided to drop by today. For our purposes, though, the cloud is a computing environment where it's difficult for you to point to the exact thing that's running your software, right? You can't really point to a specific computer. That includes both private clouds, where you might buy the hardware and run it in-house with CoreOS and Kubernetes or other similar software, as well as public shared clouds, where you rent access. But what's a cloud made out of? Well, it's made out of Linux servers, mostly. And on one hand, this is a true statement. There is no cloud, it's just somebody else's computer. The vast majority of the servers that make up the various clouds on which you might want to run software are indeed running Linux. On the other hand, it's a little misleading, because if you're lifting and shifting an application from your IT closet or a dedicated server at a colo facility to a virtual machine running in somebody's cloud, you don't care what OS or what hardware that machine is running, as long as the VM itself is doing whatever you want it to do. So we can sort of think of this as Cloud 2.0. You have the same software, it's just running somewhere else. Retroactively, we could call getting dedicated servers in a co-location facility Cloud version 1. But the shift to cloud computing isn't just taking your existing applications and putting them on VMs running on one of these machines, running in a server farm just outside Tulsa. The next step to applications living in the cloud is paring down the artifacts you deploy to only the application and its dependencies. Why do you need the overhead of a VM and keeping its OS up to date when all you really need to do is encapsulate the application logic that you've built and run only that code? So obviously that's where containers and Kubernetes come in. Containers are, we think, the fundamental technology that underpins the future of the cloud. Kubernetes then comes in as a way to fit all of these containers together to make sure that you're serving an application as a whole, as opposed to one specific task in that application. And now you've got a reproducible, hermetically sealed software artifact that you can reason about, instead of the massive surface of an entire operating system with all of the daemons running on top of it, plus the software that you actually want to run. So we can call that sort of cloud version 3.0. But I think the real point of the cloud is to have software which is built to run in the cloud. That is, distributed systems which might have tiny little pieces running in containers on each of those computers running in Tulsa. So instead of having a large chunk of each of those computers, you have APIs and services disaggregated from what used to be a monolithic whole, each of which can be pushed at its own speed and evolve as needed, doing one thing really, really well, instead of having a monolithic whole that needs to be updated every time something inside it changes. Some of those services will be private, that is business logic built for organizations for their own use. Some of it's going to be shared managed services built by cloud providers, or by API service providers also running in the cloud. So let's call that Cloud 4.0, sort of a function as a service or platform as a service. And I'm biased, because I've been working on App Engine, our cloud platform as a service product, for the last 4.5 years. That's exactly what this is. And it's the model of serverless computing that we've been offering since about 2008. I think there's a lot to be said for this, because it's also the way that Google's internal cloud works. So if software is increasingly moving into the cloud, the tools that we've relied on to deploy and manage and debug software when it's on premises become increasingly more difficult to use. We might very well not have access to a lot of the hardware infrastructure that a VM is actually running on. Instead of looking at the hardware or deep in the OS, we need to move up the stack and work at higher levels of abstraction, tracing remote procedure calls between API endpoints, building automated monitoring, for example, using Prometheus and tools like that, and debugging tools based on the flows of traffic between software services. And one of my colleagues, John Truscott-Reese, likes to put it this way. We've discovered that running a service out of rapidly changing components is different in kind from old-style system administration, and doing it well is an engineering discipline. Instead of administering systems that we can see and touch, we instead engineer services which are native to the cloud, building upon other services which are themselves native to the cloud. In order to do this, we need to build software to manage all of the software that runs our services. Not only do SREs run services, we also need to feed what we've learned about designing software for operability, that is, how to make it work effectively and reliably in production, to the application developers that we work with. One of the key points that has actually made this workable and feasible is that Google's code base is very open internally. Internally, we're almost open source. Engineers can see and propose changes to just about any piece of software. This has allowed us to mold our software to fit our needs very precisely, to instrument it so that we can understand exactly what it's doing, and so on. That's obviously a bit more challenging for people with code bases that they don't control. But with open source, with Kubernetes and with CoreOS and so on, I expect that we're going to see that standards will emerge in API call tracing, other fields, much like we've seen for data encoding and transport. So as more software is built to fit the cloud will in turn fit operability. It'll become better able to work. So Google started down this path about 12 years ago. We built an in-house cloud, Borg, and the many internal services built upon it. And then we started running our public web services, for example, search and Gmail and Docs, using our private cloud. As part of that experience, we found that we needed site reliability engineering to make our cloud services run effectively. As other people start to build APIs and services and software, which is native to the cloud, I expect we'll continue to see interest throughout the industry in building reliable software services. While 100 schools of thought may contend for exactly how to do that, I think that we'll discover that cloud-native software needs SRE, and SRE is native to the cloud. Thank you. Thanks.
So, next up, we have a speaker of a little bit of a different tack, I guess I would say. You may have noticed that with all of the CoreOS imagery, we always have a lot of things that are themed around both, the terra firma that we stand upon here, the kind of logo of the cutaway of the Earth, as well as the things that we aspire to beyond, and which drove Rocket and a lot of other things. And to help explain some of this and give us a little bit of a fun perspective on kind of other things related to space, we have a very special speaker here, Dr. Lucianne Walkowicz. So if we can get a round of applause for her, that would be fantastic. Thank you.
All right, thank you so much for having me. This has been really fun. I work on a fair number of open source projects in astronomy. I am not going to talk about any of them. I am instead going to tell you about something that is a little different, as Redbeard said, from everything you've been talking about at this meeting. I know how much you engineers love chaos, so I hope to terrify you all this morning. I'm going to talk a little bit about our sun. And I realize now that the CoreOS logo is actually the Earth. To me, that looks like a model out of an astronomy textbook. And what I wanted to talk to you about is how our sun actually affects all of the things that you've been speaking about, and particularly how it impacts our world as connected as it is. So if you were to be here in San Francisco about just shy of 158 years ago, you would see the sky at night looking something like this. So this image was taken more recently than that, but around September or so in 1859, there was an incredible display of northern lights here in San Francisco. They were notable for a variety of different reasons. For one thing, they were red. That's not terribly unusual. The more unusual thing is that they were incredibly bright, so people actually gathered outside and went to go look at the reflection of the northern lights on the bay. Further away from here in the Rockies, campers actually woke up in the middle of the night, and some of them started making coffee because they thought it was dawn, even though it was around 1 a.m. And you could see these in New York, and you could actually see them down in the Caribbean. Now, for anybody who knows anything about northern lights or is thinking about the actual words, northern lights, Typically, you don't see these displays down at low latitudes. You certainly don't see them down in San Francisco, and you definitely don't see them in the Caribbean. So what this was one of the more benign manifestations of something called the Carrington event. At the same time as the skies were glowing this beautiful fuchsia, telegraphs, the dominant communication technology at the time, were going completely haywire. There were huge currents induced into these telegraph wires, these long wires, created sparks, set fire to telegraph papers, and even induced enough current that some of the telegraph operators actually had a conversation without their machines being turned on. And it turned out that all of these effects, although it wasn't understood at the time, were all caused by the same thing. So across the planet in England, this relatively innocuous-looking orb that many of you probably recognize as the sun was being observed by an astronomer named Richard Carrington. And what he was doing, this is a more recent picture from NASA's Solar Dynamics Observatory, so we get to see all these beautiful features here, so pay attention in particular to these little freckles here, these sunspots. What Carrington was doing was making drawings. He had a projection system so that he could safely project the image of the sun and map out, as many people did at the time, where these spots were, and this was his drawing of it. And as he was making this drawing, he noticed that in addition to these little dark spots, all of a sudden there were these bright white patches on the part of the sun he was looking at. And he was incredibly excited. He'd never seen anything like this before. At first, he did what any of us do when we find something unusual, which is assume that we've broken something. Then he realized he hadn't broken anything, and he ran to go get a friend to come and look at what was happening. This is a huge mistake. When something is interesting, that's interesting is happening at the telescope, you never, ever leave the telescope, because it was basically over by the time he got back. But what he had actually observed was the largest recorded flare, solar flare, in modern history. And this flare showered our planet with energetic particles and radiation that created all of those effects that I mentioned earlier. Incredible aurorae that were bright, that lasted for days, that came down as far as our equator, the disruption to all of our communications, the fires in those telegraph papers, all of them caused by this event. And back in 1859, we were not so much of a connected society. So here today, actually a couple of days ago, this is a video of the sun over 48 hours from about the 29th of May. This is again taken by Solar Dynamics Observatory. And as you can see, we now have a considerably more detailed view of the sun than just sitting and drawing sunspots. So you can see that there's a lot of stuff happening. If you look kind of over at the limb of the sun, the edge there, you'll see these little loops, and there are dark patches and also bright patches and loops across its surface. And this is our modern view of the sun. All of the dynamic stuff that you see happening on the surface of our star is all related to the kinds of events that created the Carrington event, these solar flares. And so I'll tell you a little bit about how these work and how they would affect us if they were to happen today. So here in San Francisco, I know you have Carl the Fog, but from the standpoint of a person that lives in Chicago, your weather is beautiful and is the same all the time. So here you're used to hearing the weather report. And sure, there's a little bit of change hour to hour, but for the most part, it's pretty stable. Well, it turns out that astronomers think about what our sun is doing in terms of what's called space weather. So space weather is this catch-all term that is used to apply to anything that our sun does that impacts the environment around it, and most notably impacts our planet Earth here. A lot of the times the sun is quiet. The picture that I showed you a moment ago, that I'll show you again in a second, showed things happening on the surface of the star, but no major events. But occasionally we monitor the sun in part so that we can learn when these events will happen and know when there'll be a chance of a solar flare or even an impact from some of those energetic particles that are associated with these events that might create a geomagnetic storm and actually impact us here on Earth. So when we look at our star, we're constantly monitoring for things like these bright regions and what these loops are doing. And you'll also notice that here there's a little bit of a dark spot. Now, A couple of years ago, this can look very, very different. So the sun actually is more active or less active with time, and we're in a relatively chill part of the solar cycle. But even just a couple of years ago, you can see that our sun looked considerably different. So there's these very, very dark patches, these bright ones over here. And similar to the way that earthly weather is handled, this can create a fair amount of sensationalism. So this is today's second Reddit reference. That is not actually a screen grab of the Weather Channel, but it might as well be because I don't know what your weather app looks like. But my personal favorite up here is video, watch as your mother gets literally ripped apart by this tornado. Oh shit, your friends are dying. All the weather coverage, right, is very pearl clutchy, shall we say. And similar things happen when we talk about space weather, albeit I think with sometimes a greater amount of backing behind them. So here's a news story that happened in 2013 with such mild headlines as, yikes, a chunk of the sun is headed towards Earth at 2 million miles per hour. And why has the sun developed a huge hole? So what they're all talking about was this image right here. So this is our star. Here's one of these dark patches. It turns out that the term, because astronomers are terrible at nomenclature, the term for this is actually a coronal hole. It has a very specific meaning, but when you say that there's a hole in the sun, well, all kinds of things get wrong, especially when Fox News invites people on to talk about the hole in the sun. So I'll read you, I have not given an attribution on this quote because this person is usually a very good science communicator and unfortunately drank out of the water cooler at Fox or something. So I'll read this quote. You'll notice that part of the sun is missing. No big deal. This part that's missing, the reason it's dark, is that a whole chunk of the sun basically ripped off, blew out, and is coming our way at about 2 million miles an hour. Not at all alarmist, right? So it is true that this is called a coronal hole. However, that has a very technical meaning that is not really conveyed by those headlines. So what's going on? Okay, so it is true that our sun can influence us here on Earth. So to give you a little bit of a closer view of what's happening, so this is something we call the prominence, this sort of big loopy thing. And as you can see, it's a relatively small fraction of what's happening on our sun. But it is quite a violent event. This material that you see coming off the surface of the sun can be sprayed out into space, as I'll show you in a moment, and also can release high-energy radiation, ultraviolet and X-ray radiation. For scale, that's you and everyone you know and everyone who has ever existed in human history. So, yeah. So there's reasons to monitor our sun and to be careful, even if there's not a hole in the sun. So what's actually going on? Well, it turns out that our sun is essentially a giant magnet. At some point in your past, somewhere along the life path that led you to be in this room, you probably played with a magnet in science class. You might remember that there are north and south poles, and that there are these magnetic lines, these field lines that go through the sun itself or through a typical bar magnet. Now, it also turns out that our sun rotates, but our sun is not a solid body, right? So it doesn't rotate like a basketball that you might spin on your finger if you are better than sports than I am, where all of the different latitudes spin at the same rate. In fact, the sun is plasma. It's essentially charged particles and therefore behaves more like a fluid. And so the different latitudes on the sun actually rotate at different speeds, such that if you're up by the pole, it takes something around the pole about roughly a month to go around, whereas the equator goes around once every 25 days. And this turns out to be really important because what happens is that these lines of magnetic field that get generated deep within the star come up through the surface and they get tangled by these rotating motions. And so if we look at this in cartoon form, what you see is that those field lines get wrapped around the star and they get tangled up. And in practice, when we look at our sun, all of those loops that you see on the surface or along the edges there, all of that dynamic stuff is caused by these little loops of magnetic field coming out of the surface of the star. So if we could take a little cake slice out of our image of the sun, so imagine taking the let's pretend the CoreOS logo is actually the sun now. Take that little piece and look at it. What you're actually seeing when you see these big loops is regions where the magnetic field is sticking up and out of the surface. And so all of the stuff that we see in those movies, the bright patches, the dark patches, the loops, the changes in how they're structured, are all related to the magnetic field. Those dark spots that Carrington was drawing back these 158 years ago are actually the foot points of where those loops stick out. They appear dark in visible light. And in ultraviolet light or in X-rays, like the images that I'm showing you here, you can actually see some of the bright, sort of tenuous material that gets stuck in those loops. And so these sunspots are just one aspect of what we can observe, but also these prominences, the loops themselves, and these flares that happen, because it happens that the magnetic field actually has a little bit of tension, so it can snap and rearrange like a rubber band. And we can watch this happening in real time. So this was the Bastille Day flare. So this is back from 2000. And I have this picture of a slinky here because you can imagine this, what I'm about to show you, as these loops being lined up in what we call an arcade. So you get many of them together, and you could get this sort of chain reaction where many of these loops light up and all affect each other. And these kinds of things happen all the time. Back in 2000 or 2001 or so, it was a very, very active time on the sun. And right now, we're in a very chill cycle again. But we will be eventually back to having these flares on a more regular basis. So back to that wonderful moment of science communication where everybody was told that the sun had ripped off a chunk of itself and was flying towards us. Actually, what it means when we say that there is a coronal hole or when you see these dark or light patches on the surface of the star, it all has to do with the star's magnetic field. So if you look here, so this is a map of where the field actually is on the star, and you'll see there are some of these big loops, like I told you before, but then there's also these lines that sort of stream off into space. And it turns out that when you have those closed loops, they trap that bright material, and you get these bright, sort of loopy-looking structures like that. But when they're open, then you don't have any of that bright material trapped. And so it is true that some of that material gets thrown off into space or out towards us sometimes, but it's not a hole in the sun. So if you leave with nothing else, there's no hole in the sun, and there probably never will be. However, it is also true that the sun affects us. So let's look at this a little bit more in detail and think about how this might impact us now that we're a society that has a small computer in all of our pockets and relies on things like the internet, which is essentially a manifestation of many, many different aspects of technology coming together. When we see these things that our sun is doing, these can have impacts here on Earth. So if we zoom out a little bit, so the previous video was from the Solar Dynamics Observatory, which takes these beautiful high-definition movies of the sun. They're available all the time. You can go look at what the sun is doing right now if you want to. This is actually from a different satellite called SOHO, and it's considerably further away from our sun. So right here is this sort of blue patch there is just a disk that's used to block out the brightness of the sun. That's Venus, not a UFO, if anybody's wondering what the heck that is. But the circle in the middle here, that's actually the entire disk of the sun. So what you're seeing right now is the zoom out of all of that material flying off our star and out into space. And if you watch this long enough, all of those sort of staticky looking things, that's actually impacts from energetic particles from that flare hitting us sort of right in the face, or at least hitting the satellite right in the face. But this can happen here on Earth as well. So despite the fact that this is not to scale, so just to insert 94 million miles in between this star, it's a little hard to put these things on scale. The idea is that as our sun has these flares or the ejection of particles, which are called coronal mass ejections or CMEs, they can get launched out towards us and end up impacting our planet. And this bluish stuff that you see around this illustration of our planet here is our planet's magnetic field. Now, this is a wonderful thing for us to have. For the most part, it acts a little bit like a shark cage that prevents a lot of that stuff from impacting us directly. So we get a fair amount of shielding from the fact that we ourselves have a magnetic field, and we also have an atmosphere. So in the case of radiation, a lot of that ultraviolet radiation, for example, gets stopped by interactions with oxygen in our upper atmosphere. However, it can still create a fair amount of havoc here on Earth. So, for example, one of the things that can happen is those beautiful aurorae. So this is from the International Space Station. It's a little dark, and I apologize for that. But this green glow that you hear is what the aurora or the northern lights look like from space. So this is caused by some of those energetic particles coming in. They spiral around our magnetic field, and they impact the planet's atmosphere and cause it to glow up by the poles. So there's northern lights, there's also southern lights, and this is why you don't usually see things like the aurora down in San Francisco or down by the equator. However, if you get a big enough solar flare, you do see those things. And so the Carrington event was essentially a gigantic flare that was able to send enough energy down that it affected the entire planet's atmosphere and not just the area by the poles. Now, the other thing that I like this video for is that it has hints of some of the other stuff that we care about since we've been a spacefaring society and a technologically enabled society. And what you see here is our power grid, right? This is our lights at night that are visible from space. And of course, for every street light that you see there, there's a myriad other technological pieces of whatever, that's a very technical term, technological pieces of whatever, attached to this power grid, right? So as a technologically capable society, these kinds of solar storms can be very bad for us. So one of the biggest effects that we've experienced actually just within the past couple decades is the influence of solar flares on the power grid. So if you think back to that anecdote that I told you at the beginning of this talk about the Carrington event and how the dominant effect at the time was these induced currents in the wires that were used for telegraphs. Well, that's fine, but nowadays we have not only long-distance wires for communications, but we also have a very, very interdependent power grid. And what can happen is if we end up dumping a lot of current into that, it can actually overwhelm a lot of our infrastructure. And in general, like many, many aspects of large-scale infrastructure in this country and others, the grid is very, very old and very fragile. And this was actually from a flare that happened in 1989. So the entire province of Quebec was in blackout for almost 24 hours when this flare took place. But this transformer is actually in New Jersey, and it was completely melted. Now, yes, damage to infrastructure is a big deal, but actually what's more worrying is not just that it can be damaged, but how long it can take to recover. So in this particular case, this was just one transformer. But transformers cost tens of millions of dollars and can take up to a year to manufacture. And they're not really something that's just hanging out like out back of the rest of the power plant. And so while you can take steps to mitigate some of these effects, if they actually do take place and if you suffer real damage, you can have parts of the grid be affected for much longer than the duration of the flare, for example, if it's damaging enough. And it turns out that in addition to just our grid, there's all kinds of different effects that can happen. So in 1859, we weren't a spacefaring civilization yet, but we are now, and we rely on satellites for all kinds of things. Probably most notably, all of us rely on this for GPS, right, and for position information. And one of the things that can happen when you have a solar flare is that you can get these induced currents in the upper atmosphere, and that can create what's noted here as GPS scintillation. So essentially, usually with GPS, you can be accurate to about a meter or so, but this creates big uncertainties because it's very difficult to lock on to the signal of where you are. In addition, some of those energetic protons can actually, or energetic protons, electrons, any kind of particle, can interact with actual infrastructure here in space. So you not only have the danger from induced current, but actually particle impacts as well. And in addition to that, you even have danger from induced current in submerged or embedded infrastructure under the ground. So this could really create havoc in a lot of different systems, and it's not just the cutesy stories about people setting fire to their telegraph paper anymore. So naturally, you'll be pleased to know that our government is aware that this is a problem. This is a report from the National Academy of Sciences that was done, lead author was Kapperman, called Severe Space Weather Events, Understanding Societal and Economic Impacts. This was the sort of Weather Channel version of, of reports of this nature, in that this was a very dire warning to the government, to all of scientists working on these kinds of pieces of infrastructure, that what you're seeing here is the interconnectedness of our power grid. And circled in these dark sort of black lines are regions of probable collapse in the event of a Carrington event type thing. So one of the sort of weird things about the United States power grid is that actually a lot of power that comes to you in, for example, Los Angeles is generated many thousands of miles away. There's a really good book called The Grid that just came out. I'm blanking on the author right now, but it just came out this year, and it's really interesting about the development of our grid, and I highly recommend you read it. In the meantime, what I'm sorry to tell you is that because we have such an interconnected and fragile grid, that while, and I'll touch on this in a moment, while there are effects to your actual electronics directly and to the storage of your data, one of the biggest threats is actually just these induced currents and their ability to damage our power grid. Because you can have a cell phone that still operates because it wasn't plugged in, it didn't get its circuits overwhelmed. But if you can't charge it, or if you can't actually use it to make a call because all of the supporting infrastructure no longer works, then congratulations on not frying your cell phone, I guess. So one minor silver lining here is that this was the most dire of these reports, and I put this next bit specifically in for all of you. So JASON, which is a study group, was called upon by the Department of Homeland Security to do a complementary report and to see whether this analysis was quite as bad. So the JASON report is considerably softer in tone, but I wanted to particularly point out to you this quote, that while the impacts still remain severe, quote, "We are not convinced that the worst case scenario of the previous report is plausible, nor is the analysis based on using proprietary algorithms suitable for deciding national policy." So I thought this was a nice thing, and this is a great link, I think, to the way that I, as an astronomer, think about open source, is that for us, astronomers and particularly people who work on studying things that might impact actual national policy, reproducibility is a big thing in science. And so for astronomy, having code and having data be available is essentially the equivalent of our Bunsen beakers or our ability to buy equipment, because the tool that you develop your insights out of is actually a software tool. It's not something that's a physical piece of equipment in your lab for the most part. And so this is a nice thing, I think, that one of the reasons to maybe not worry so much is that you can't reproduce this because it's not done with open source tools. So, however, there are ways of mitigating some of these effects. So you can, shield. You can build better relays, essentially, that will help make your grid not so interdependent. And a lot of Scandinavian countries, for example, have implemented solutions that shield them because they're at higher latitude. They have to think about space weather more often. But for the rest of us, one of the problems is just a lack of organization. There's nobody in charge of making these changes. It's not really a national priority, and therefore it just sort of goes along, and that's fine for now when the sun is in this relatively chill portion of its life. But within a couple of years, we'll be back towards the more active portion of the solar cycle, and we'll have more of this to think about. So I did want to also mention that your data storage is directly affected by these events. So these things called single event upsets are interactions between energetic particles and transistors. And there's this little funny balance that happens where as transistors have gotten smaller and smaller, remember this is like a physical interaction where something impacts your transistor, you get a bit flip, and your data is actually corrupted. So the smaller you build a transistor, the better off you are because it's literally a smaller target. Unfortunately, integrated circuits are composed of many, many, many transistors. And so the more of these you use, then it doesn't matter so much whether they're individually very small. And so you could do certain workarounds. One of the examples that's often shown is that you could build everything in triplicate, for example, and then have a voting system where an impact is unlikely to happen in more than one at a time. And therefore, if you have two that are telling you the same thing, then you can probably trust that. However, that's, of course, an increase in cost. And frankly, it's mostly off the radar for a lot of consumer electronics. So these errors that you're sometimes likely to ascribe to things like software bugs or just your actual hardware, your phone's being stupid, you can't do something that you want to do. In some cases, these are actually related to energetic particles from space, which sounds cool, but is still a big pain in the butt. So I just wanted to leave you with, if you're interested in this stuff, I was interviewed for a movie called Lo and Behold. This is a Werner Herzog documentary that came out that's about the internet. If you want a linear description of the history of the internet, this is not the movie for you. If you've ever seen a Herzog documentary, linear descriptions of history are not really his forte. However, if you'd like to learn a little bit about some of the ways that human beings and our technology and our connectedness interact, this is an interesting portion of that. And I especially wanted to include this image because I'm at the Adler Planetarium in Chicago, and this is taken from our doorstep, these monks using cell phones. So I highly recommend that you check it out. And I'm going to wrap it up here. But if you ever want to ask me a question, you wake up with a burning need to know something about black holes in the middle of the night, or apparently don't ask me if you want to feel better about solar flares because everybody started this talk laughing and now everybody looks really depressed. Sorry. But you can find me on Twitter. I'm Shakalulu, and I'd be happy to take any questions that you have there or maybe during the break. Thanks.
And now we move on to the kind of regular portion of our program. I wanted to take a few minutes just to, kind of cue folks up for kind of what's going to be going on for the rest of the day, as well as to kind of thank some of our sponsors here for a moment. Though, at the end of the evening today, we are going to be having a hack night, which is sponsored by Microsoft, specifically working around Helm. So if you're interested in learning how to write Helm charts and everything, that would be really, really good because it's going to be a hands-on opportunity to be able to work through that and get both help and help other people who have an experience with that. For our sponsors, I'd like to thank IBM. I would like to take a moment to thank Google Cloud Platform, Microsoft Azure, AWS, the CNCF, OpenStack Foundation, Compose, Worker, Tigera, Sysdig, Datadog, Instana, Wavefront, Aqua, Buoyant, and Twistlock. Thank you so much for all of the kind of resources that you've been able to provide us to and really make things as special as possible for our attendees today. So thank you very much, and now we move on to a little bit of a coffee break and the rest of our program.